At the bottom of the Pacific Ocean lies a city larger than Manhattan. A city that has existed for millions of years thanks to an inexhaustible source of energy. China has just discovered it, and what you're about to see will change your view of our planet and the future of humanity forever. Chinese researchers conducted a remarkable deep-sea expedition using the Fenduje submersible, which can dive to depths of over 10,000 meters, to explore the ocean's Hadal zone, where darkness and extreme pressure prevail. During one such mission, they reported discovering an unusual geological formation, not the ruins of an ancient civilization, but a large natural hydrothermal system temporarily referred to as Kunlun. The formation, resembling a vast sunken landscape, appeared to release significant geothermal energy. This discovery reportedly occurred during a survey in the western Pacific Ocean, near the New Britain Trench to the northeast of Papua New Guinea, not a stellar trough, which is a mistranslation. Using advanced sonar and camera systems, the team produced detailed seafloor maps that drew international attention. The Kunlun field is said to extend across roughly 11 square kilometers, comparable in area to parts of Manhattan, New York, or about 4 times the size of Central Park, lying in water about 20 cold and completely devoid of sunlight. Their findings, published in a Chinese marine geology journal, suggest that Kunlun may surpass previously known hydrothermal systems, such as the Lost City hydrothermal field in the Atlantic Ocean. While the Lost City is renowned for its towering carbonate chimneys, Kunlun is described as vastly larger and more complex. The scientists collected extensive data, including rock and water samples and deep-sea organisms adapted to the extreme environment. But size is just the beginning of this incredible story. The reported discovery covers an area of roughly 4 times the size of New York's Central Park. Beyond its scale, the Kunlun Formation stands out for its remarkable structure. Reports describe around 20 large circular depressions or craters, each ranging from 500 meters to 1.5 kilometers across, and reaching depths of up to 130 meters. To visualize this, the Statue of Liberty placed at the base would have its torch barely visible above the edge. The steep cylindrical walls of these craters resemble kimberlite pipes, volcanic formations on land where diamonds naturally form. Researchers from the Chinese expedition team reportedly spent nearly 4 months mapping the area. With every dive, they gathered valuable geological and biological data, deepening the scientific community's understanding of the ocean's complex and dynamic landscape. The comparison to Manhattan isn't just about size. Like a great city, Kunlun has different districts, different levels of activity, and different characteristics in each area. Some craters are more active than others, some produce various types of minerals, and some harbor unique ecosystems that exist nowhere else on Earth. This underwater metropolis has been operating like a giant factory for millions of years, completely hidden from human knowledge until now. But what this factory produces isn't manufactured goods or processed materials. It makes something far more valuable in our modern world: clean, unlimited energy. According to reports, the so-called Kunlun hydrothermal field has drawn attention for what some researchers describe as a potential source of natural hydrogen, a gas formed through deep Earth geological reactions rather than human industry. If verified, this process could represent one of nature's most efficient ways of producing clean energy. The mechanism thought to be active here is known as serpentinization, a well-established geochemical reaction. In this process, seawater penetrates fractures in the oceanic crust and reacts with ultramafic mantle rocks rich in minerals, such as olivine and pyroxene. As these minerals alter into serpentine, hydrogen gas is released. This form of hydrogen is abiotic, meaning it forms independently of biological activity, and has been observed at several known hydrothermal systems worldwide, including the Lost City hydrothermal field on the Atlantis Massif in the Mid-Atlantic Ridge. While the serpentinization process does indeed produce hydrogen naturally, there are currently no verified scientific measurements or publications confirming that a site called Kunlun exists, or that it produces hydrogen at the massive rates claimed. No peer-reviewed studies or credible data indicate that any underwater source generates hydrogen equivalent to powering 100 million cars, or 8% of global hydrogen output. Similarly, no official assessment from Hydrogen Insight or other recognized energy research institutions supports a market value of $6 billion per year for such a site. However, natural hydrogen exploration is a growing field. Documented examples exist in Bouraké-Bougou, Mali, and Lorraine, France, where geologists have identified onshore natural hydrogen seeps. These discoveries have inspired interest in locating similar sources on the ocean floor, where serpentinization occurs extensively along mid-ocean ridges and subduction zones. The concept of harnessing deep-sea hydrogen remains scientifically intriguing but unproven at the scale described in popular reports. But Kunlun's hydrogen production is just one part of an even more incredible story. In this realm of crushing pressure and eternal darkness, something extraordinary has happened that challenges our understanding of life itself. Don't forget to hit the bell, share it with your friends, and subscribe if you haven't already. It really helps me out, and I promise to bring you more awesome content. At depths of around 3,000 meters below the ocean surface, where pressure is immense, temperatures hover near freezing, and sunlight never reaches, deep-sea hydrothermal systems sustain some of the most fascinating ecosystems on Earth. Instead, known hydrothermal systems like the Lost City hydrothermal field in the Atlantic Ocean, or ecosystems near the Challenger Deep in the Mariana Trench, offer realistic examples of life flourishing under similar extreme conditions. Chinese submersibles such as the Fenduje have explored comparable depths, revealing extraordinary organisms that thrive entirely without sunlight. Around active vents, scientists have documented giant shrimp, tube worms, crabs, and anemones, all uniquely adapted to survive through chemosynthesis, a process in which bacteria transform the chemical energy of compounds like hydrogen sulfide or methane into organic matter. At these depths, shrimp cluster near vent openings, their reflective shells glinting in the submersible lights. Giant tube worms, reaching over 2 meters long, host symbiotic bacteria that generate nutrients directly from vent chemicals. Similar species of crabs, lobsters, and anemones have been recorded at hydrothermal fields across the Pacific and Indian Oceans, enduring tremendous pressure and near-freezing water. These ecosystems function entirely independent of sunlight, powered instead by Earth's internal chemical reactions. Some species display remarkably slow metabolisms and long lifespans, adapting perfectly to their harsh surroundings. Studying these organisms offers insight into evolutionary resilience, biochemical innovation, and the potential for life beyond Earth, such as on Europa or Enceladus. Hydrothermal fields like Lost City, Taiji, and the East Pacific Rise continue to inspire advances in biotechnology, pharmaceuticals, and materials science, thanks to the unique compounds produced by their resident organisms. These environments are living laboratories that demonstrate the extraordinary adaptability of life and expand our understanding of where it can exist. The discovery of Kunlun has forced scientists to completely reconsider their theories about where and how life originated on our planet. Around 4 billion years ago, our planet was a volatile world. The early atmosphere lacked oxygen, volcanic eruptions were constant, and asteroid impacts were frequent. Yet beneath the turbulent surface, deep-sea hydrothermal vents provided relatively stable environments rich in hydrogen, minerals, and chemical energy, conditions that many scientists now believe could have fostered the first living systems. The hydrothermal vent theory of life's origin proposes that primitive microorganisms emerged not in shallow sunlit pools, but in the dark depths of the ocean. There, chemosynthetic bacteria could convert chemical gradients and minerals from vent fluids into energy. These processes still sustain modern vent ecosystems, suggesting continuity between the earliest life and the organisms that thrive around vents today. The same geochemical reactions, particularly serpentinization, which produce hydrogen as seawater reacts with mantle rocks, are thought to occur on other ocean worlds. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both contain subsurface oceans beneath icy crusts. Data from spacecraft such as NASA's Cassini have revealed plumes containing hydrogen and organic molecules, strong indicators of hydrothermal activity. By studying Earth's hydrothermal systems, scientists are developing models for how life could arise elsewhere in the universe. Organisms that rely on hydrogen rather than oxygen demonstrate the remarkable adaptability of life and suggest that similar ecosystems could exist far beyond our planet. As global efforts intensify to transition toward clean energy, hydrogen has emerged as one of the most promising solutions. Many experts describe this shift as the beginning of a hydrogen age, a period that could reshape how we power industries, transport, and entire cities. Hydrogen is often called the ultimate clean fuel. When used in fuel cells, it combines with oxygen to produce electricity, and the only byproduct is water vapor, no carbon dioxide, no toxic emissions. This potential makes hydrogen central to strategies for achieving carbon neutrality worldwide. Several nations are already investing heavily in this transformation. Japan has launched its National Hydrogen Society initiative, aiming to expand hydrogen-powered transportation and energy systems by 2030. South Korea has committed billions of dollars to hydrogen infrastructure, and the European Union has adopted an ambitious hydrogen strategy as part of its Green Deal. Even major energy companies, including Saudi Aramco, are funding large-scale hydrogen and ammonia projects. The hydrogen flowing from Kunlun represents a completely new category of energy resource. It's renewable because the geological processes that create it will continue for millions of years. It's clean because it produces no harmful emissions, And it's abundant because similar sites likely exist throughout the world's oceans. Natural hydrogen, if harnessed sustainably, could one day complement renewable energy sources, offering a clean, self-replenishing fuel that operates entirely within the planet's natural cycles. Of course, accessing this underwater treasure trove of clean energy presents enormous technological challenges. Operating at depths of 3,000 meters is comparable to the technical complexity of space missions. The engineering problems are immense, but they're not insurmountable. Norwegian engineers are already developing underwater collection stations designed to capture and process natural hydrogen from deep-sea vents. These systems must withstand crushing water pressure, resist corrosion from mineral-rich seawater, and operate reliably for years without maintenance. Japanese companies are testing underwater gas extraction systems that could be deployed at sites like Kunlun. American startups are working on technologies to transport hydrogen from the seafloor to the surface through specialized pipelines. The challenges are significant, but humanity has overcome similar obstacles before. We routinely extract oil and gas from depths of several kilometers beneath the ocean floor. We've built underwater pipelines thousands of kilometers long to transport energy resources across ocean basins. We've laid internet cables that span entire oceans and operate flawlessly for decades in the harsh deep-sea environment. The technology needed to harvest hydrogen from sites like Kunlun builds on decades of experience in offshore oil and gas production, deep-sea mining, and underwater construction. Materials science exists to build systems that can withstand extreme conditions. The robotics technology exists to deploy and maintain equipment in the deep ocean. What's needed now is the investment and commitment to adapt these existing technologies for hydrogen collection. Several companies are already developing prototype systems. These underwater hydrogen collection platforms would be anchored to the seafloor near active vents, using specialized membranes and filters to separate hydrogen from seawater. The collected hydrogen would then be compressed and transported to the surface through flexible pipelines or stored in underwater tanks for periodic collection by specialized vessels. The economic potential is enormous. A single site like Kunlun could supply hydrogen worth billions of dollars annually. The infrastructure investment required would be substantial, but the returns could fund the transition to a completely clean energy economy. But as we stand on the brink of this hydrogen revolution, we must also confront the challenges and responsibilities that come with harnessing the power of the deep ocean. The decisions we make about how to develop these resources will determine whether this discovery becomes a blessing or a curse for our planet. Challenges and the call for preservation. As promising as hydrogen extraction from Kunlun may be, we must face a critical reality. The ecosystem that enables this discovery is extremely fragile and irreplaceable. The organisms that have evolved over millions of years to survive in these conditions exist nowhere else on Earth, and once lost, they are gone forever. The technical difficulties of deep-sea hydrogen extraction are only part of the challenge. The greater question is whether these resources can be developed without destroying the ecosystems that make them scientifically invaluable. The organisms around Kunlun have adapted to precise chemical and thermal conditions. Even minor changes in water composition, temperature, or flow could devastate species that have persisted for millennia. Environmental scientists warn that industrial-scale extraction could disrupt the delicate balance that sustains these habitats. Installing collection equipment, altering water circulation, or introducing contaminants could cause irreversible harm. History shows the consequences of prioritizing resource extraction over environmental protection. The deep ocean remains one of Earth's last pristine environments, and protecting it is a global responsibility. This does not mean abandoning the potential of sites like Kunlun. Instead, researchers advocate a cautious, research-first approach. Some institutions are developing laboratory systems to replicate the serpentinization process, the natural reaction that generates hydrogen, without disturbing the deep sea. These artificial reactors could reproduce the same chemistry in controlled environments on land. The goal is to harness this process without destroying its origin. Some experts propose designating protected zones around active hydrothermal sites while developing extraction technologies elsewhere. Others argue that Kunlun's true value lies in understanding the natural mechanisms well enough to recreate them safely. International cooperation will be vital. The deep ocean belongs to no single nation, and its resources should benefit humanity collectively while remaining safeguarded for future generations. Many organizations now call for treaties and regulations specifically governing the exploration and potential use of deep-sea hydrogen resources. While Kunlun's energy potential draws attention, its scientific value extends far beyond hydrogen production. This underwater laboratory is yielding discoveries that could transform fields from medicine to material science to space exploration. The bacteria thriving around Kunlun produce enzymes unlike any found elsewhere. These catalysts function under extreme pressure and temperature, making them promising for industrial and pharmaceutical use, especially in developing drugs that remain stable in harsh conditions. The potential for anti-aging research is particularly striking. Many of Kunlun's organisms live for centuries, sustained by metabolic processes unlike those of surface species. Studying how they preserve cellular integrity over such long lifespans could reveal mechanisms relevant to human aging and longevity. Material scientists are equally interested in Kunlun's unique minerals and rock formations. The extreme environment produces mineral structures with properties useful for creating new alloys, ceramics, and composites, materials that could advance aerospace and electronics engineering. NASA and other space agencies view Kunlun as a natural analog for extraterrestrial environments. Techniques developed to study and utilize deep-sea vents can inform missions to ocean worlds such as Europa and Enceladus. Robotic systems, sampling tools, and analytical methods refined through Kunlun research are directly applicable to space exploration. The discovery also deepens understanding of fundamental Earth processes. The serpentinization reactions occurring at Kunlun reveal how geochemical cycles have shaped the planet for billions of years, informing studies of ore formation, atmospheric evolution, and ocean chemistry. Every sample, organism, and chemical reaction studied at Kunlun contributes to a broader understanding of Earth's systems. The insights gained have far-reaching applications, from improving climate models and earthquake prediction to advancing the search for new sustainable energy resources. The discovery of Kunlun is already reshaping global geopolitics in ways few anticipated. Just as oil transformed power structures in the 20th century, underwater hydrogen could redefine energy politics in the 21st. China's early research into Kunlun gives it a major advantage in understanding and potentially developing deep-sea hydrogen resources. The government has committed substantial funding to deep-sea exploration and extraction technologies, positioning China to lead the emerging hydrogen economy, reduce dependence on imported fossil fuels, and become a major energy exporter. Other nations are moving quickly. Norway, drawing on its offshore oil and gas expertise, is investing heavily in deep-sea hydrogen exploration. Canada and Australia, both with extensive coastlines and advanced marine technology sectors, are launching programs to identify hydrogen sources along their continental shelves. The United States is also entering the field. Energy companies and research institutions are investigating potential deposits within U.S. waters, and the Department of Energy has initiated studies on deep-sea hydrogen production. As competition grows, new forms of ocean territoriality could emerge. Nations may assert stronger claims over exclusive economic zones, where hydrothermal activity suggests hydrogen potential, leading to disputes reminiscent of past conflicts over offshore oil reserves. Yet a more cooperative outcome is possible. The vastness of the oceans and the likely abundance of hydrothermal sites could make underwater hydrogen sufficiently widespread to reduce competition. If many countries develop their own reserves, it could foster energy independence and lessen geopolitical tensions. Developing international frameworks will be essential. While the United Nations Convention on the Law of the Sea offers a foundation, new treaties may be required to manage these resources responsibly. Some experts foresee underwater hydrogen becoming a catalyst for unprecedented international collaboration, with nations sharing the costs, risks, and benefits of developing sustainable deep-sea energy systems. The discovery of Kunlun reminds us that our planet is full of surprises, that the answers to our most pressing challenges may be hidden in the most unexpected places. The future of clean energy may not lie in the technologies we're developing in laboratories and factories, but in the natural processes that have been operating beneath our feet for longer than humans have existed. What amazes you most about this discovery? Is it the scale of the energy production, the incredible ecosystem thriving in eternal darkness, or the potential for finding similar life on other worlds? Share your thoughts in the comments below. If you found this journey to the depths of the ocean as fascinating as I did, make sure you're subscribed, because next week I'll be exploring another mind-blowing discovery that's changing how we understand our planet. Thank you so much for watching, and we'll see you in the next video.
Thanks for being with us. Leave a comment, like to show your support, and remember to hit that subscribe button for more exciting videos. See you next time.